Hey there, and welcome to this explainer. Take just a quick second to look around you right now. The screen you're watching this on, the chair you're sitting in, the water in your glass, the trees outside, the stars in the night sky, and yeah, even your own hands. Absolutely all of it, everything in existence, is made of these ultimate, invisible building blocks called atoms. Today, we're going to completely dissect the very foundation of the universe. Let's get into it.
Trillions upon trillions. I mean, just let that number sink in for a second. That represents the sheer, almost incomprehensible scale of the microscopic world we're about to explore. Whenever we discuss atoms, we're dealing with quantities so incredibly massive that our human brains honestly struggle to even process them.
So, to make that abstract scale a bit more personal, let me ask you this. How many atoms do you think make up your own body? The answer? Trillions upon trillions. You are essentially a walking, talking, breathing galaxy of these incredibly tiny particles, and they're all working together in perfect harmony just to keep you alive.
To really ground that staggering math, think about a standard wooden pencil. Just on the very tip of that pencil, you could fit millions of atoms. Millions! It's like, if you take a stone and break it down into smaller and smaller pieces, you eventually hit a point where it simply cannot be divided anymore while remaining the same substance. That absolute smallest unit right there, that's the atom.
Now, as you can probably guess, it took humanity a really long time to figure this out. Way back around 400 BC, an ancient Greek philosopher named Democritus first proposed that matter is made of indivisible particles. He called them atomos, which literally translates to indivisible. He didn't have any scientific proof, just a brilliantly correct idea. Jump all the way forward to 1803, and John Dalton introduces the first modern atomic theory, showing that atoms combine in fixed ratios. And then, by the 1920s, absolute giants of physics like Bohr, Schrödinger, and Einstein revealed the deeply strange quantum mechanics of the atom. They showed us that these particles don't just move in simple little circles, but actually exist in these complex, fuzzy probability clouds.
All right, so let's move on and take a look at the anatomy of the atom itself.
First thing to know, an atom is definitely not some solid little ball. It's actually overwhelmingly just empty space. If you were to blow up a single atom to the size of a massive football stadium, the dense center, which we call the nucleus, would only be the size of a tiny glass marble, sitting right on the 50-yard line. Yet, despite being just a tiny marble in a massive stadium, that little nucleus contains almost all of the atom's weight. No way, right?
So, what's inside that super dense nucleus? Well, first up resides the proton. Protons carry a positive charge of +1, and they essentially act as the ultimate ID badge for any element. The number of protons entirely dictates whether an atom is hydrogen, oxygen, or solid gold. If you change the number of protons, boom, the entire element changes.
Sharing that extremely tight space inside the nucleus is the neutron. And just like the name sounds, a neutron has zero charge. It is completely neutral. But don't let that fool you. It has a massive, absolutely vital job. Because protons are positively charged, they naturally want to repel each other. They want to push away. The neutrons step in to act as the ultimate nuclear glue, stabilizing those protons and keeping the whole nucleus from just flying apart.
Finally, zooming all around the vast empty space of our stadium at incredibly high speeds, we have the electrons. Electrons are tiny, way smaller and lighter than protons, and they carry a -1 charge. You can kind of think of electrons as the energetic social butterflies of the atom. Their specific arrangement way out in the outer limits determines how electricity flows and exactly how the atom bonds with other atoms to create chemical reactions.
To see how all this perfectly comes together, we just look at the atomic number, which is simply the total number of protons an atom holds. Take hydrogen, for example. It's the lightest and most abundant atom in the whole universe, and it has an atomic number of exactly 1, just one single proton. And that perfectly defines the simplest element we know of.
Now, calculating the mass of an atom, it's actually really straightforward addition. You just count what is inside that nucleus, protons plus neutrons. Take carbon-12. It has 6 protons and 6 neutrons, giving it a neat mass of 12. Oxygen-16 has 8 of each, resulting in a mass of 16. It's really just simple math.
Okay, let's clear up a very common point of confusion in chemistry: the difference between an isotope and an ion. Atoms of the exact same element can sometimes have different numbers of neutrons. We call these variations isotopes. For instance, hydrogen always has 1 proton.
But if it happens to pick up some extra neutrons, it becomes a heavier isotope called tritium. The mass changes, sure, but it's still hydrogen. On the flip side, an ion is all about those social butterfly electrons. If an atom gains or loses electrons, its overall electrical charge changes. Sodium losing an electron becomes a positive ion, while chlorine gaining one becomes a negative ion. And when those opposites inevitably attract, they bond to form something entirely new, like the regular old table salt you put on your fries.
And hey, speaking of those electrons, they don't just buzz around in total random chaos. They occupy very specific energy levels called electron shells. The very first shell, the K shell, can only hold 2 electrons. The next one out, the L shell, can hold 8. Now, listen closely, because here's the absolute secret to all of chemistry. Atoms are constantly seeking stability, and to get it, they desperately want their outermost electron shells to be completely full. This intense, never-ending drive for stability is the root cause of literally all chemical bonding.
Which brings us to our next stage, building the universe. Because atoms naturally seek those full electron shells we just talked about, they join forces to form molecules. Let's follow a recipe. Take 2 hydrogen atoms, introduce 1 oxygen atom, and as their outer electrons interact and share space, they bond. Boom, you've just created H2O, water. You took 2 invisible gases and combined them to create the exact liquid that makes life on Earth possible. Add 1 carbon and 2 oxygens together instead, and you get carbon dioxide.
Now, how these molecules behave physically in our world relies entirely on how tightly packed the atoms are. This is what dictates the states of matter. In a solid block of ice, the atoms are super tightly packed together. Add some heat, which ramps up the atomic motion, and they start moving a bit more freely, becoming a liquid. Add even more heat to the mix, and the atoms spread apart rapidly, becoming a gas. This beautifully simple atomic motion is exactly what explains the melting, freezing, and evaporation we see around us every single day.
Let's bring this explainer right back home to you. Your incredible physical body is mostly made of just 4 types of atoms: oxygen, carbon, hydrogen, and nitrogen. But obviously it doesn't stop there. The hard rigidity of your bones, that comes from calcium atoms. The ability of your blood to carry life-saving oxygen up to your brain, that relies entirely on iron atoms. Even your DNA is simply a highly precise, magnificent structural arrangement of atoms. Every single heartbeat, every breath you take depends completely on these atomic interactions happening right now beneath your skin.
But we have to mention, there is also an immense hidden power locked within these microscopic structures. Some heavy atoms, like uranium and radium, are unstable. To finally find that stability they crave, they release massive, unbelievable amounts of energy straight from their nucleus. This is what we call radioactivity. When we figure out how to harness this nuclear energy, we can power entire cities, treat severe diseases in modern medicine, and even push spacecraft further into the void of space. But, as we well know, uncontrolled nuclear reactions can be incredibly dangerous. The literal power of the universe is locked inside that tiny, tiny marble.
So, atoms really are the hidden architecture of everything, from a tiny grain of sand on the beach to a massive, spinning galaxy. For all the students tuning in, especially those of you learning with Ghauri Education, mastering the atom is absolutely the first step to mastering all of science. Because when you truly understand the atom, you finally begin to understand the universe. You are literally a walking universe. You are made of trillions of tiny, perfectly balanced structures, holding you together, moving your muscles, and powering your mind. So, as we wrap up this explainer, I want to leave you with this final, provocative thought to chew on. Knowing the incredible science and the ancient history running through your very veins right now, what will you build with your atoms today?